Researchers at Google DeepMind have recently unveiled an exciting new development in artificial intelligence. This new development is called differentiable MCMC layers. This innovative framework has been designed with a specific purpose in mind. Its main goal is to significantly improve how neural networks handle complex decision-making tasks. These tasks often involve discrete choices, where solutions must be selected from a finite set of possibilities. This is a common challenge in many real-world problems. The introduction of these MCMC layers promises to make neural networks more powerful and versatile in tackling such scenarios. This is a big step forward for AI. This groundbreaking work is the result of a collaboration. Researchers from Google DeepMind worked together with experts from ENPC, École Nationale des Ponts et Chaussées. Their joint efforts led to this new AI framework, announced in May 2025. The primary focus of differentiable MCMC layers is on problems typically found in operations research. These include demanding tasks like vehicle routing, which involves planning the best paths for delivery vehicles. Another example is job scheduling, where tasks must be assigned to resources efficiently. These problems are known for their complexity and the need for precise, optimal solutions under strict rules. Before this new framework, integrating discrete combinatorial solvers with neural networks was a significant hurdle. Combinatorial solvers are tools designed to find the best solutions to problems with many possible combinations. Many of these problems are classified as NP-hard. This means that finding an exact solution can become incredibly time-consuming as the problem size grows. Neural networks, on the other hand, learn through a process called gradient-based learning. Making these two different approaches work together seamlessly has been a long-standing challenge for AI researchers. This difficulty limited the application of neural networks in certain domains. Older methods for tackling these combined problems often relied on using exact solvers. While accurate, these exact solvers can be very slow and require a lot of computational power. This makes them impractical for large-scale or time-sensitive applications. Another approach involved using continuous relaxations. This means turning discrete problems into continuous ones that are easier to handle with gradient-based methods. However, this can lead to solutions that are not perfectly accurate or that do not fully respect the hard constraints of the original problem. These limitations highlighted the need for a new, more efficient, and theoretically sound method. The core problem that differentiable MCMC layers address is a fundamental one in AI. It is the difficulty of making neural networks good at discrete decision-making, especially under strict constraints. Many real-world problems are not about predicting a continuous value, like the price of a stock. Instead, they involve choosing the best option from a set of distinct possibilities. For example, deciding which specific route a truck should take involves discrete choices at every intersection. Or in a factory, deciding which machine should perform which job is also a discrete decision. These choices must often follow very specific rules or constraints. Neural networks are very good at learning patterns from data. They use a method called gradient-based learning. This method works well when the relationship between inputs and outputs is smooth and continuous. However, discrete problems involve choices that are not smooth. A small change in input can lead to a completely different optimal discrete solution. This makes it hard to use standard gradient-based learning directly. Trying to force these problems into a continuous mold often leads to solutions that are not ideal. They might not be the truly best option, or they might even violate some of the critical rules. The new approach using differentiable MCMC layers offers an innovative solution. It cleverly transforms local search heuristics into differentiable layers. Local search heuristics are smart searching strategies. Examples include well-known methods like simulated annealing or Metropolis Hastings. These heuristics explore possible solutions by making small changes to an existing solution. The differentiable part means that these layers can be seamlessly integrated into neural networks. They can work with the gradient-based learning process. This is achieved by using Markov chain Monte Carlo (MCMC) methods, which are powerful statistical techniques for sampling from complex distributions. These MCMC layers operate directly on discrete combinatorial spaces. This means they are designed to work with the actual discrete choices of the problem. They do this by mapping problem-specific neighborhood systems into what are called proposal distributions. A neighborhood system defines which solutions are considered close to a current solution. The MCMC layer then uses this to intelligently propose new candidate solutions. A key benefit is that neural networks can integrate these powerful heuristics without needing to run an exact computationally heavy solver for the entire combinatorial problem during training. This makes the learning process much more efficient. The functionality of the MCMC layers is based on established principles from MCMC methods and local search. Local search heuristics are responsible for proposing neighbor solutions. These proposals are based on the specific structure of the problem being solved. For instance, in a vehicle routing problem, a neighbor solution might involve rerouting one vehicle or swapping two stops. The MCMC acceptance rules then play a crucial role. These rules decide whether to accept a proposed new solution or stick with the current one. This ensures that the process is correctly sampling over the entire space of possible solutions, guiding the search effectively. A key feature of this framework is how it handles potential biases. Approximate solvers, which are faster but less accurate, can introduce bias into the solutions. The MCMC acceptance rules are specifically designed to correct for this bias. This ensures the theoretical soundness of the approach. It means that even though approximations might be used within the layer, the overall learning process remains robust and principled. This correction mechanism is vital for trusted decision-making. Importantly, this is achieved while also reducing the overall computational burden compared to methods that demand exact solutions at every step of the learning process. The MCMC layer is designed to approximate a target distribution of feasible solutions. It then provides unbiased gradients for a single iteration. This is achieved under a specific type of loss function known as a target-dependent Fenchel-Young loss. This technical detail is important because it allows the neural network to learn effectively. It means the network can get meaningful feedback even from a small amount of exploration by the MCMC process. This efficiency is a significant advantage. It enables learning with a minimal number of MCMC iterations, sometimes even using just a single sample per forward pass through the network. Embedding this MCMC layer within a neural network architecture has profound implications. It allows the entire model to be trained end-to-end. The neural network learns to predict good parameters for the combinatorial problem that the MCMC layer is trying to solve. For example, it might learn to predict which parts of a routing problem are most critical. Over time, as the network trains, the quality of the solutions generated by the MCMC layer improves. This synergy between the learning capabilities of neural networks and the structured exploration of MCMC methods leads to better overall performance on complex, discrete tasks. The effectiveness of the differentiable MCMC layers was rigorously tested. Researchers evaluated the method on a challenging, large-scale dynamic vehicle routing problem. This problem also included time windows, adding another layer of complexity. Such problems are very common in logistics and delivery services. The performance of the MCMC layer was compared against existing perturbation-based methods. These methods involve making small, random changes to solutions to explore possibilities. The results of these evaluations were very promising and demonstrated clear advantages for the new MCMC approach. This shows its practical value. In these tests, the MCMC layer significantly outperformed the perturbation-based methods. This was especially true when the time available for computation was limited. For example, in scenarios with restricted time budgets, the MCMC layer achieved a test relative cost of 5.9%. This was better than the 6.3% achieved by anticipated baselines that used heuristic-based initialization. This improvement indicates that the MCMC layer can find better solutions more quickly. This is crucial for real-world applications where decisions often need to be made fast. The ability to perform well under pressure is a key strength. The performance difference became even more striking under extremely tight time constraints. When the allowed computation time was very low, for instance, just 1 millisecond, the MCMC layer method still managed a respectable 7.8% relative cost. In stark contrast, the perturbation-based approaches struggled significantly, showing a relative cost of 65.2%. This massive difference highlights the efficiency and robustness of the MCMC layers. Furthermore, the researchers found that initializing the MCMC chain with good starting points such as ground truth solutions or solutions enhanced by other heuristics improved learning efficiency and the final solution quality, particularly when using only a few MCMC iterations. In conclusion, this research provides a principled and effective method to integrate NP-hard combinatorial problems into neural networks. Crucially, it does so without relying on computationally expensive, exact solvers. The differentiable MCMC layers, constructed from local search heuristics, allow for training that is both theoretically sound and highly efficient. This development successfully bridges the gap between the powerful learning abilities of deep learning and the rigorous methods of combinatorial optimization. The potential transformative effects on AI are substantial. This framework could fundamentally change how neural networks address discrete decision-making. This will make them far more applicable and powerful for solving a wide array of complex, real-world problems, leading to smarter and more optimized systems across many industries.